All right. Confidence intervals. Let's talk about them for a second. So we're in chapter 8. Confidence intervals. We're kind of at the big stuff. Well, especially chapter 9, hypothesis test. That really is the big deal. So we're kind of moving into the big deal. Basically, the rest of this course is going to be confidence intervals and hypothesis tests. So we're going to lay the foundation. We've kind of got all the groundwork already laid with probability and all the terminology, you know. And so now it's time for the real stuff. We're going to basically learn how do you do confidence intervals this week and maybe a little bit next week, and then how do you do hypothesis tests. And those are the two big deals. We'll take an exam on that. The next exam is just 2 chapters, just chapters 8 and 9 because they're so important. Confidence intervals and hypothesis tests. That'll be the 3rd exam, and then in the 4th exam, we'll take those and we'll do confidence intervals and hypothesis tests on all kinds of other things. So basically, the rest of the course is confidence intervals and hypothesis tests. So what is a confidence interval? Well, what do you think? What do you think the average on the exam we just took is? Average on exam 2. I don't remember off the top. I don't think I even looked at it. But anyway, we can just guess. I mean, you're totally blindly guessing because you didn't see all the numbers. But I saw all the numbers, but I still didn't. I'm still sort of guessing too. So anyway, we might say, hey, I think the exam 2 average is between, I don't know, somewhere between 60% and 80% and 80%. Maybe the average, the exam you guys just took, maybe if I figured out the class average, I could probably go on Canvas and it would show me the class average, was somewhere, so I'm saying this means, what the meaning of this thing, let me explain. This little parentheses I put, it means, well, I keep changing my mind, we're going to write it. It means from 60% to 80%. I don't know really if the real class average is in there. Probably pretty safe bet. Like I might say to you, hey, I'm 90% confident. You can see I'm building up to the word confidence interval. I'm 90% confident that the real, in fact, maybe just write it over here, be a little bit better. Maybe I'm 90% confident, sure, that the real average is in that interval. Does that make sense? We all understand that idea of what I'm saying. I might say I'm 90% sure, and that's probably about where I am at. I'm about 90% sure that the real average on that exam we just took, not knowing it exactly off the top of my head, but just having looked at the scores, is somewhere between 60 and 80%. Like it might be 69%, it might be 73%, it might be 75%, it might be 65%. I'm pretty sure, I'm 90% confident it's somewhere between 60 and 80%. Now think with me. What if I was to try to make a statement, a more precise statement? Because that has a range of 20 points, doesn't it? From 60 to 80. That's a pretty wide gap. What if I said, hey, I'm really sure it's between 65%. Well, here, let's make it even more narrow. Let's go 68% to 72%. I'm saying I think that the average, the true average, the real average on exam number 2 is somewhere from, between, we can just say between, between, same thing, between 68% and 72%. Now, just give me your real life feel. How confident would you be, or I be, about that more narrow statement? Would I be more sure that the real average is in there? Like, again, I don't know exactly what the true average is. It's somewhere around that. So I said, hey, I'm 90% sure that the average is between 60 and 80 on exam number 2. What if I said, hey, I think the average is between 68 and 72. That's a more narrow, there's only, 4 degrees there? So would I be more sure or less sure? My knowledge hasn't changed. All I've done is I've kind of glanced at the scores. Like I told you, that's really the truth. I've just glanced at them. I never saw the actual average. And so if I tried to make a statement that's more narrow, a smaller interval, would I be willing to bet more money on this? Let's just do it with money, because that's where we see, like people say, put your money where your mouth is, right? Say, are you really sure? So do you think, in which case would I be more willing to bet money? How about that?
The top.
Yeah. I'd rather bet my money on the wider interval, because that's more likely to catch the real average, than making a more narrow statement. Because the average might be 67 and not quite be in that interval. Or 73 and not be between 68 and 72. Whereas it would have been captured by the first interval, Is that making sense? So when you make a more narrow statement, you're going to have what? Higher confidence or lower confidence? Lower. Yeah, you might say, I'm only 70% confident that the real average is in that interval, because it's a more narrow interval, It's in a more narrow interval. So I'm just giving you the feel. This isn't what we're going to, this is the feel. I'm giving you the feel before we dive into the particulars. Just want you to feel, because we're going to do them the next 10 weeks. The rest of the semester is confidence intervals and hypothesis tests. So we'll do a lot of them in a lot of different situations. So I want you right from the get-go, I'm always trying to get you in tune with your math feelings, right? That's always my desire, that you should feel the math, because that's just going to be the most helpful to you. That'll lead you well in a million situations if you just really sense what it is we're doing. So you get the idea, right? We're trying to make an interval, and we're stating with it how sure we are, how confident we are that the real average is somewhere in the interval. Now, we don't know the real average, do we? Not me included. None of us know the real average on exam number 2. But we're basically taking a guess. That's what a confidence interval is, right? We're making a statement. We say, we really think the real interval is between 60 and 80. The real average between 60 and 80, or maybe, if we're really sure of ourselves, maybe between 68 and 72. But that's a risky statement. We're going to have less confidence in saying a more narrow statement. So that's the name of the game. That's what we're wanting to be able to do. That's very useful in statistics, is to be able to make a confidence interval on something done in real life. This is what they do all the time. They want to measure something in the real world. Say they have some new medical treatment, and they're saying, okay, we have this new medical treatment, and let's say the old treatment brought about, let's say 70% of the people were cured from whatever infection they had or whatever, with the old treatment that we've done for, 100 years, or maybe not that long, 50 years or whatever, okay? And then suppose there's a new medical treatment, but it's new. They haven't done it for years and years, so they're not really sure yet. Maybe they've only done it on, 120 people. They did some trial, when the FDA, the Federal Drug Administration, tries out some new drug or something. So they tried it on 120 people. And for those people, let's say 80% were cured. 80% were cured from their infection or whatever it is they had. So why don't they just say, well, that's it. The new treatment cures 80% of the people. It's better than the old treatment. It's good. We're done. Yeah, the problem is, what about luck, Like I've said several times. That's always the problem. How do you know that you just, they're not all healthy, but maybe a good portion of them, maybe 30 of them were just really healthy people. They were going to bounce back if you just gave them drinking water, They were going to get better anyway. And it wasn't really the treatment. And that's all it would take. Not even 30. What if it was just 20 people? And really, maybe the new treatment only heals 75%. Maybe it's a little worse than the old, or that's better still, Maybe it only does 68%, let's say. Maybe that's the real rate of cure. And we'll know that 10 years from now, after, because eventually you'll know the truth, right? After you give this new treatment to thousands and thousands of people and years go by, then you're like, oh, whoops. Yeah, now that years and years have gone by, we really know that the new treatment only cures people 68% of the time. The old one was actually a little bit better. Why'd we get fooled? Well, it must have been that original group. There was just a few, got kind of a lucky or unlucky, as you want to call it, sample. We just happened to get people that were kind of more healthy, at least some of them. All it would take, 10%. What's 10% of 120? 12, right? 1/10 of it, 12. So all it would take is 12 people, and you're going to throw the thing off by 10%. 12 people that are just super healthy. They caught the infection for a little while, but they're going to bounce right back, having nothing to do with the medication, on their own because they're super healthy. All that would throw it off by 10%, wouldn't it? So do you see the problem in real life with trying to determine things, using statistics as a tool to help us figure out what's true? Is this new medical treatment really better? Is this new business plan really better? Is this new scientific method really better? How do we know? Well, the problem is you can try it out for a while, but there's always the luck problem, isn't there? The random. And we've rolled dice and done things. We see that there's randomness. And so what they do instead of that is they make a confidence interval statement. Instead of saying the new treatment is 80%, cures 80% of the time, when they've only done it on 120 people, they would say something like, we think the new treatment is somewhere between, so they would take the 80, and what they would do is they would give or take 10%. Say, I'll make up a number. It'll be, maybe it'll be, let's say 9%. They'll give or take 9%. They'll say, we think it's 80. We did 120 people and 80% of them got better, but we realized there might have been a little bit of luck in that, but probably not all luck. I mean, it couldn't have been all 120. It could be, but that's 1 in a million, right? That's certainly not. So luck can affect it a little bit, but not a ton. So what if they said, we really think 80% is the new treatment's cure rate, but we know there could be error in our sample because we've only done 120 people and luck can get in there. So we're going to say, give or take 9%. So if you take 80% and you give or take 9%, that could be as high as 89, right? 80 plus 9. And it could be as low as what? 80 minus 9? 71%. You tracking what I did there? I just took 80 minus 9 and 80 plus 9 to get those two numbers. I took the 80% and I give or take 9%. So that means, and we might say, you know what? We're 90% sure, confident. We're 90% confident that the real true average, for the new treatment, the cure rate, which we will know a few years from now. After we've done thousands and thousands of people and years have gone by, we will know the truth. We will know really how good the new treatment is. And we're 90% confident, sure, that after all that time has gone by, the real average will be somewhere, let's say, between 71 and 89. In other words, 80, give or take 9. And all those numbers are higher than 70, the old treatment. So we would say, hey, that's a good statistical evidence to make a change to the new treatment. See how they think? See how confidence intervals help us form decisions? So they don't just come out with this 80% number right off the bat. They got to talk about the fact that there could be error in that. And how much error? Because of random luck. And that's what a confidence interval is all about. Because what if it was give or take? What if they had only done like 20 people? What if they'd only done 20 people? Do you think that would make a broader interval or a more narrow interval? With the same confidence, we still want to be 90% sure of where the real average is. Would that make us make a more narrow statement or a wider statement? Yeah, it's gonna be wider. Are you dialing in with me on the? Are you starting to feel it? Are there math feelings rising? A little bit, I'm hoping. Right? Let me flesh it out, and I think that'll help. Right? Because if you only did 20 people, wouldn't there be more chance of error than 120 people? You tracking with me? If you only did, or let's lower it even way down. What if we say, yeah, we only tried the new treatment on 10 people. Now there's a lot of chance of error in that. If you're only doing 10 people, you could have got half of them really lucky healthy or lucky unhealthy, either way, you know. You could have got a weird 10 people, or at least 8 out of 10 or 5 out of 10, that's really throwing your sample off, you know what I mean? Whereas if you get 100 people, there's less chance that all 100 or even half the 100 are weird people, right? Y'all feel that, right, with the probability. Kind of like when we flip the coin, right? Remember the law of large numbers? Remember when we did the coin flipping thing? And I said, hey, if you flip it once or twice or 5 times, you could get all heads. It's possible. If I flip 5 times, I could get all heads, right? But if I flipped it 100 times, I'm not going to get all heads. It's just never going to happen, right? So that's the idea. More numbers make the chance of weirdness go down, because any weirdness will kind of balance out, won't it? So if we have and this is what we're going to be doing throughout our problems. They'll have a certain number of subjects that are examined. So if you only look at 10 people, you're going to have more chance for error. So you might say give or take 20%, say, instead of just 9. So then that would go from 80 minus 20 to 80 plus 20. So it might go from 60 to 100%. Then we might say, yeah, we think the new treatment is 80%, because that's what it did on the 10 people, 8 out of 10, got better. But we realize there could be a lot of error when we only look at 10 people. So we're going to give or take 20%, meaning we're 90% confident that the real average that we'll know after years and years of the new treatment is somewhere between 60 and 100% are cured. Now, the problem with that statement is it may be higher than 70, it may be lower. Do you see the problem? We wouldn't be sure, would we? Or even 90% sure that the new treatment's better, because we're saying it could be between 60 and 100. So maybe it's 65. If it's 65, it's lower than the old treatment. If it only cures 65% of its patients, then it's worse than the old treatment. And by this statement, we're saying it's somewhere between 60 and 100. Maybe it's 100. Yeah, maybe. But maybe it's 61. You see the problem with that statement? We wouldn't want to change our medical practices unless we were pretty sure that it was better than the old treatment. If the old treatment's 70, this may be something lower than the old treatment. Somewhere between 60 and 100. That's not a very good statement, is it? It could be 62, and that's worse than the old treatment. So we'd like to be able to say an interval that's all higher than 70%. Well, can't we, though? Can't we just make a more narrow statement? I mean, the average came out to be 80 here. Didn't it come out to be 80? Isn't that the middle? It is. And can't we make a lower error statement, like 5% or something, and say it's 80 minus 5 or to 80 plus 5? In other words, that it's 75 to 85? Yeah, we could, but you know what will happen to your confidence then? Are you starting to feel this? Think with me. We only gave the new drug to 10 people. Only 10. And and 8 out of 10 got better, so 80% cure rate, which is better than the old that we've been doing for years and years. But we realize, and we're saying we only want a 5% error. This is how they do these studies. They said we want the number, we only want a 5% error. So that, because we know this isn't perfect, there could be error, we could have got a lucky group. So give or take 5%. So take 5%, give 5%, 75 to 85. So we're thinking the real average for the new treatment that we'll know years down the road after 1,000 patients. We think the real average is going to be between 75 and 85% of the people are going to be cured. But how sure are we? Do you realize our confidence level would go down the tubes? We would become like 20% confident. Why so low confidence? Because we only looked at 10 people. We're not really very sure that the actual interval is in there. So you would only be able to say we're only 20% confident that the real average is between 75 and 85 and thus higher than the old two. We're only 20%. That's what would happen in that situation. So what do you got to do to get the confidence level up and the interval to be narrow? That's what we want, huh? We want both those things. We want to have a narrow interval so we can really say something without huge whopping error statement in there. And we want to say it with confidence, 90%. You never be 100%, right? Because there's always the chance of crazy, crazy luck. But you'd like to be 90% confident. 95, you're going to put affecting people's health, and you're spending millions of dollars on medical equipment. So what can get both of those things higher at the same time? Are you feeling it? What would you have to do in this study? So we gave 10 people the new treatment. 8 out of 10 were healed. We want a 5% error, but we want a higher percentage of confidence. More test subjects. That's always the answer, huh? If instead you said, let's try it on 500 people, and it still came out 80%, then you would be like 95% confident. Could you get a lucky 500 people? Almost no way. It's just not going to happen, huh? And we've seen the probability of large numbers. It just doesn't happen. So you're getting the feel for how this works. So there's 3 elements we'll play with in the confidence interval game. The number of people that are tested, the more the better, right? The more people you've tried out the whatever on, the new treatment, the new business plan, the new whatever, the more confident you're going to be. And you'd like to make a narrow statement with small error. There's always some chance for error, some chance for luck. But the more narrow, the better, and the higher your confidence, the better. A bigger number of people will make your confidence go up, and your interval be more narrow, so you can make a more precise statement about what you really think the new treatment's going to do over the next 5 years. That's the feel. That's confidence intervals for the next 8 weeks. All right, so let's do some actual homework now. So there it is. A smartphone manufacturer, not as exciting as new manufacturer, but smartphone manufacturer is interested in constructing 90% confidence for the proportion of smartphones that break before the warranty. So what portion break before the warranty? 91 of the 1679 randomly selected smartphones broke before the warranty expired. So what can we say about that? All right, so you get the idea. So you get what's happening. This is, by the way, this is what companies do. Who was it that was telling me? I don't know if it was somebody in here, one of my other classes, I can't remember now, was telling me their friend or brother or somebody did testing in one of these labs. I can't remember who it was now. It was a couple months ago. But yeah, there's people paid to do this. And all they did all day long, I can't remember what they were testing, some piece of computer equipment or something. And they would just pick up a new one, try out the thing, and then put it down, try it again, put it down, try it again, put it down, and wait how long till the thing broke. A little bit of a boring job probably, but it was a tester of equipment. And so that's what companies do because they want to know how long is their stuff going to last before it breaks. So let's say they tested, 1679 smartphones, and they gave them to people to use for free to test them out. And 91 broke before their warranty period, so they had to, the company had to pay to replace the phone. So they're thinking, all right, 91 out of the 1679 phones broke. So, so what percentage is that, by the way? You guys got that in the calculator? Let's figure that out. What percentage is that? 91 divided by 1679. I'm getting 5. Now I got 0.054. So 0.054. So that's 5.4% basically. So just over 5% of the cell phones broke before the warranty. So they're thinking, about 5% of the cell phones. But the companies would calculate ahead of time, where do we want to put the warranty? How much do we want to offer? How much are we going to pay? So they're basically thinking we're going to have to pay for about 5% of the cell phones out there are going to go bad before the warranty. Can we afford that? Are we still going to make profit? This is how business would use statistics to calculate where they want to set warranties and stuff. But here's the problem. Maybe those were a weird 1679 or 91. Maybe the sample was weird. Maybe luck got in there. Maybe those were people that were very abusive on their cell phones. I've seen people like that. My son throwing it around all the time. So, right? Maybe they weren't very careful people, or maybe they were super cautious people, and kept the thing in a cover in a case and wrapped in styrofoam all day long, and really a bunch more of them are going to break than that, and that was just a super careful group. That could happen, right? Maybe that was a random group. So maybe they were lucky careful or lucky careless, and the reality is that it's a much higher percentage that are going to break, or a much lower percentage in reality that's going to break. There's always the chance of luck, right? So they want to make a 90% confidence interval. They want to become 90% sure on what the true average. They're going to find out a year from now when this phone hits the international market, right? And millions of people purchase it and use it for a year and break and file for the warranty. They'll know. And then it'll be too late if they made a bad business decision and 20% of those phones come back wanting warranty. They're going to, some managers are going to get fired, aren't they? And the company's stock is going to plummet, and this stuff is going to matter, right? So they want to know with some confidence, 90% confidence ahead of time. That 5.4%, that's what happened in the sample. But there's always air in there. How much air could there really be? How high or low could it really go with 90%? We want to be 90% sure on what the range is really going to be. Is it going to be somewhere between like 4% and 6%? You get the idea, right? 5.4 is going to be the middle. And it's going to give or take. It's going to go below that and above that a little bit, right? Because it could be a little bit lower than that. Could be a little bit higher than that. It's going to be around 5.4. Our answer is going to be something like, 4% to 6%, or 3% to 7%, or something like that, our 90% confidence interval. All right, with that in mind, how do you find it? How do we do everything in this course? We let technology do it, right? We just got to know the buttons to hit, which is great, because that's real life. We can do it on computers. But let me show you how to do it. All right, so let's go to our first screen, and we will do it. 91 out of 1679. Okay, so here we go. So number one, 91 out of 1679, right? 1679. Right. Okay, so, and we want to do a 90% CI, confidence interval. All right, how do we do it? You pull out your handy-dandy TI 8384, and let me give you the instructions for it. So you're going to, guess what button you're going to hit? You're going to hit the stat button. Not a big surprise there. Hit the stat button and go over to the right twice to the tests menu and hit enter. Is this our first time visiting the test menu? It is. We'll live here in the next 9 weeks. Everything's going to be off this menu, basically from this point forward. We're going to do like all those things you're seeing in that menu. You're going to learn almost all of them for the different kind of things we're going to do. So in this one, we want to go down to one proportion. Where is it? One proportion Z interval. So go down, down, and find one prop Z interval. Because we're trying to find a proportion interval. I'll explain as we go. So find that menu, go on down to there and hit enter. It's A. I think it's letter A, isn't it? Yeah. On down to A. So just go on down. Find that one prop Z interval. Hit enter there. On one prop Z interval. Everybody finding that? And you get a little menu which says X and N and C level. All right. And so guess what X is? X is that 91. And guess what N is? What is N in every statistics problem? Total number of times you tried the whatever. It's the 1679, huh? So you just put those two in. And what C level do we want on this one? 90%. We want to be 90% confident. So just type in point, but you want the decimal there. So 0.90, and then hit enter on the calculate. It's as easy as that. Hit enter. And it cranks out a confidence. Let me write for you what I got. I'm getting the confidence interval 0.04511, comma, 0.06329. Y'all getting that confidence interval? 4 decimals, so I'll go, okay, 0.0451, 0.0633. That makes sense? Those are the two. So we're saying we're 90% confident that the real average, during the next 5 years of using this cell phone, will turn out to be somewhere between, that's like 4.5% and 6.3%? We're 90% sure that in time, we'll find out that the real average is between 4.5 and 6.3, right? In our little sample, we already said that it was, 5.4%, right? Because 91 out of 1679 was 5.4%. So we're saying it's between, what were those numbers again? 0.0451 and 0.0633. Notice that 5.4% is the exact middle of that. I mean, in a minute we'll figure out the exact middle. It is. 5.4, which is what we said, was that the portion they got from their sample is right in the middle. So we went down about 1% and up about 1%. That was the error. The error was about 1%. In a few minutes, we'll calculate that error on other problems. Just giving you the feel right now. Does that make sense what we're doing? So this is what a business would actually do. This is how Apple, before they release iPhone 29 or whatever, and this is what they at 11 now, right? It's just getting crazy. You're going to run out of digits pretty soon. All right. So this is what companies do. They test things, but you're never 100% sure. Isn't that the problem with all statistics? Do you see why I want to call that the subtitle of the class? Statistics, or what about luck? Right? That's the whole class. Is we're always saying, yeah, but what if that was a lucky group? And what's the chance of that? And how much would that throw things off? Right? That's always what we're always going on imperfect knowledge beforehand, and then we will know, a few years down the road, but it'll be too late then. So they want to go, okay, well, right now it looks like somewhere between 4.5% and 6.3% of the phones are going to break during the warranty. We're 90% sure it's in that interval. Let's answer the other questions. If many groups, now they're trying to trick you here, so let me track you careful on these words. If many groups of 1679, that's the number we did, right? We sampled 1679. Randomly selected smartphones are selected. In other words, if they just keep doing 1679 smartphones and sampling another 1679, many groups of those, then a different confidence interval would be produced for each group. Huh? You tracking with me? If they took another, or tracking with them, I guess, if they took another 1679 phones at random, hey, let's test another 1679, they wouldn't get exactly 91 break again. They might get close. Might get 85, might get 102, might get 200. I'd probably not, but you're probably not going to get exactly 91. You're going to get a little bit different results, right? Because of luck, because of randomness, right? About what percent of these confidence intervals will contain the true population proportion of all smartphones that break before the warranty? And we'll get to the other percent. Wait, did I just read that right? About blank percent of these confidence intervals will contain the true population proportion of all smartphones that break before the warranty expires, and about blank percent will not contain the true. So this is the not, this is the will. Does that just seem like gibberish? Let me help with that. And you'll get used to it after, because they're going to say the same thing every time. So in other words, let me ask it in a better, more meaningful way. What's the chance that 5 years down the road, after millions have bought this smartphone and used it, and they find the true percentage that break within the warranty period and need to get refunded? What's the chance it's really going to be in this interval? What's the chance it's really going to end up, when the truth is known years down the road, hey, really, it turns out 4.7% of the phones break within the warranty period. That would be between 4.5 and 6.3, wouldn't it? 4.7. Or 5.2 or 5.9 or 6.1, those would all be between 4.5 and 6.3. But what if it turns out to actually be 6.5? That's not in the interval. That's worse than they were expecting. Or maybe 4.2, better than they were expecting. It's only 4.2. So what's the chance when the truth is known years from now that the real true average will be somewhere in the interval they came up with? That's exactly it. That's what the confidence interval is saying. It's saying there's a probability. That's why we studied probability as a foundation for this. Because everything we do, confidence intervals, hypotheses, are all about probability. All stats is about probability. We're saying there's a 90% probability. So it's not guaranteed. It's not guaranteed. Truth is, it could be outside that interval. And time will tell. But there's a 90% chance. That's what it means to do a confidence interval. You're 90% confident because there's a 90% probability that the real true average, when it's known years from now, will be in that interval between 4.5, 4.5, and 6.3. So what do you put right here? 90. Yeah, 90. It's just whatever number they said there. There's a 90% of the different intervals you do are going to have the true thing in them. That's exactly what we're saying. 90% of the time, your interval is going to contain the real thing. And what percent will not contain it? If 90% of the time it's in there, what percent of the time is it not in there? 10%. Done. Those will always be that way. Those will always be whatever. Sometimes we'll do an 80% confidence test. Then this first one will be 80, the other one will be 20. So those are automatic. You won't even think about them anymore after a while. But it might be helpful too. Is that good? Am I making sense on that? Want to try another one of these? Yeah. 2. So giving a test to a group of students, the grades and gender are summarized below. The grades and gender are summarized below. Let P represent the population proportion of all male students who receive the grade of C on this test. Use an 85% confidence interval to estimate P to 4 decimal places if possible. Have you noticed their grade examples are kind of, what's the word? They're always making the males do better. Have you noticed that? That has not been my experience. I can tell you. In 20 whatever years, almost always my top students are females. And not always, but almost always. Anyway. Funny. So, all right. So, the P represents the population proportion. All students receive grade of C. 85% confidence interval to estimate to 4 places. So, anyway, all we got to do is grab those 2 numbers. Let's grab those 2 numbers that we need out of there. What are those 2 numbers? So, we're talking about the male students who received a C. How many males got a C? 12. Out of what total? 29. Out of 29 male students. Right? Because they want us to figure the proportion of male students who got a C. Like what portion of the male students got a C? 12 out of 29 got C's. So basically, that's your X, that's your N. Go do an 85% confidence interval test. Go to your TI. Go to the TI 8384. Go to the stat test. Hit stat. Go over to where you're going to go for the next 2 months. Go to the test thing. Tests, I guess it's plural. Tests. Go down to the 1 prop Z interval. 1 prop Z, because you're doing a proportion interval. And put in the X is 12. The N is 29. The confidence level 0.85. And hit enter. I'll do it too. And you get the magic numbers. I'm getting, how many places? 4 places again. I'm getting 0.20, no, that's an 8. 2821. 2821. 2.5. 5, 4, 5. I guess we got to round that last one to a 5. I'm getting 5, 4, 5, 4, 5. But I guess you got to round that fourth one to a 5. There we go. Y'all getting that okay? We're saying we're 80% confident that the real percentage of males that get a C overall in that material is somewhere between 28% and 55%. Good question. So yeah, so if they say something like 99.5%, you got to turn it into a decimal, so just move it back 2 places. Okay. So it'd be 0.995 in the C level. Yeah, just always move it 2 places. Good. Other questions on that one? Okay, so number 5. We wish to estimate what percent of adult residents in a certain county are parents. Out of 200 adult residents sampled, 180 had kids. Based on this, construct a 90% confidence interval for the proportion of adult residents who are parents in this county. Express your answer in try-inequality form. That's such fancy talk, isn't it? I put my answer in try-inequality form. That just means, same thing we've been doing all along. I'm not going to quiz you on those names. So it just means there's 3 parts. That's why the try. Anyway, same thing. Just do the same thing is all they're saying. So what do I mean by same thing? Well, so we're going to go to go to the 1 prop Z interval. Go to stat and tests. Stat and tests and 1 prop Z interval. And then what is your, can you tell on this one, what's your X on this one? 180. 180 had kids out of, N's always the total, right? Total number, we try. 180 out of 200 had kids. Confidence level, 90%, they said. 0.90, hit enter, and it'll crank it out for you. And so I'll do it too. I'm getting, how many decimal? 3. 0.865 to 0.935. Y'all getting that okay? So track with me on this, because this is one that's a little different. All that's the same. Nothing new there. But now comes the new part I want to show you about. Is they're going to also ask me to put it in this other format down here, which is kind of like the give or take error format. So I want to take the answer we just got, the 0.865 to 0.9. Everybody good to there so far? We're saying we're 90% confident, 90% sure that the real average, right, because they only looked at 200 adults. They just surveyed 200 parents in this county. Now, they didn't ask every parent in the county. But they just surveyed 200 adults and found that 180 had kids. And so they said, we're 90% sure that the real average, or the real percentage, I could say average, real percentage of adults that have kids in the county is somewhere between 86% and 94%. So we're 90% sure. So that's so now can we make that as a percentage give or take error statement? Same truth, said another way. So let's think about, I think it'd be helpful if we think about backwards and then forward will make more sense. What if I said, and you'll read this sometimes in the paper, or nobody reads the paper, huh? Look online news, and you'll see sometimes where it says 80%, the studies show that 80% of the adults in Fresno County or whatever county, Tulare County, of the 80% of the adults have kids, are parents. But it's 80%, margin of error, give or take 10%. Sometimes they'll say it that way. So give or take 10% or margin of error, 10%. Sometimes they'll call it that. Margin of error. Because, again, no study's perfect. There's always the chance of luck. And so that's what they're doing. They're giving a confidence interval, basically, when they say margin of error, 10%. What they mean is that 80% is their best guess, but there's chance for error. The real average for everybody in the county might be different because the sample could have been just lucky, one way or the other. So to find the range, you've got to give or take 10%. So that would be 80 minus 10 and 80 plus 10. In other words, 70 to 90, huh? You with me on that? Now, we want to go backwards. Do you see what we're wanting to do? Right, so this is what? This would be 70. This equals 70 to 90, doesn't it? 80 minus 10 is 70. 80 plus 10 is 90. So we're saying that the real percentage of adults that have kids are somewhere between 70 and 90%. We want to be able to work backwards from this kind of a statement, because that's what we have right here, back to this kind of a statement, because that's what they're asking me for. So how do you go backwards? How do you go backwards from like a 70 to 90 back? You got to find the 80 first off. What could you do? You guys tracking with me?
Average?
Yeah. Right, Bryce? Do you all see that? Let's look at it again. So again, we said, okay, they think the average is 80%, give or take 10. So that means subtract 10, add 10, they think it's between 70 and 90. So now think, how could you go backwards from the 70-90 answer back to the 80, give or take 10, if you just had the 70-90, because that's what they're asking me to do. So if you just had the 70-90, how could you find the 80? Do you see it's the middle of 70 and 90? Do you see that? See how 80 is the very middle of 70 and 90? How can you find the middle of two, right? Isn't 80 right in the middle of 70 and 90? So you see, when you have the two numbers, the way to find the front number, and we'll get the other one in a minute, the way to find the front one is to find the middle of these two. And how do you find the middle of two numbers? What if you got a 70 on your first exam and a 90 on your second? How would you find the middle? Like where your grade is overall right now? Yeah, we know. It's called average. You add them and divide by 2, don't you? That's how you find the middle of two numbers. You add them and divide by 2. So you would just add these two and divide by 2. Find their average, huh? And that'll give you the middle. Does that make sense? And then how do you find the 10% part? So if we added those two and divided by 2, 70 plus 90 divided by 2, we'd get 160 over 2. We'd get 80, as promised. And then once we had that 80, we said, okay, 80 is the middle. 80 is the middle of 70 and 90. Right? Am I writing too small? Let me try again. So if you had 70 to 90, and you said, hey, I want you to give me whatever, give or take whatever. I want you to change it to that form. First thing we would do, step 1 would be to average them, right? 70 plus 90 divided by 2. 160 divided by 2, 80. We'd pop an 80 there. That'd be our first step.
Where'd you get 10 from?
Oh, yeah, that's what I'm trying to figure out right now. Yeah, so how would we find that 10? That's exactly where I'm at. So far so good. Somebody said, hey, the interval goes from 70 to 90. First thing I would do would be to average them, get 80. That's what we start with. That's what we found there. And then, yeah, step 2, how am I going to get this error amount? If you have 70 and 90, and now you know their middle is 80, how far is that from the one in the front? How far is that from the one in the back?
10%.
Yeah, and how are you coming up with that?
It's just the difference between the 70.
It's the difference. Take the middle minus the small one, or the big one minus the middle one, whatever. Right? It's how far, it's 80 minus 70, isn't it? That makes sense? You just take the one in the middle and subtract the small one. Does everybody see that? If I gave you, one more time, if I gave you 70, I really want you to feel this, because they're going to ask you to do this a lot, and you can memorize steps, but it's way better if you just start to feel it. So if I gave you 70 to 90 as an interval, and I said, hey, I want you to find the middle, which is the average, and then the give or take error amount, what you would do, step 1, is just find the average. Find the average. So the average would be 80, right? Add them and divide by 2. So you'd find the middle. So if you have 70 and 90 and 80's in the middle, then step 2, You're basically saying 80 subtract what and add what to get 90. 80 subtract what? So if you're at 80, what do you have to subtract to get 70? 10. You got to go back 10. And what do you got to add to get 90? You got to add 10. How do we find that 10? Well, we just know 80 minus 70 is 10, huh? See what I'm doing there? You take that average and you subtract the small number. You find the jump from the middle back to the small number, which is going to be the same jump as from the middle to the big number, because it's the middle. It's the same amount to either edge, isn't it? And that's how you find the error amount. 80, give or take 10, is the same as 70 to 90. Does that make sense? Alejandra.
Where did you get 70 from? Are you getting it the coefficient number, like that percentage, or are you getting...
Oh, I just totally made these up.
Okay, but I know, but in our problem...
Okay, so in our problem, I'll go back and do our example. I just made up 70 to 90 as nice even numbers. Yeah, it doesn't apply to our example at all. I'm going to go back and it's the same process though. So do you see, I'm just trying to pick easy numbers, totally made them up. Totally made up easy numbers to give you the feel of the operation. Sorry, am I confusing you because there's no 70 and 90, there's no problem? I should have said, these are different numbers. All right, so does everybody see the process? So whatever numbers they give you, do the average and do the average minus the small. So let's go back. So here's our actual numbers, not 70 and 90. Not at all. And let's do the real numbers. So, all right, so what do we do? Let me erase all these false number things. That whole time, were you thinking, where do you get the 70 and 90?
Yes.
All right, so what do we do? So step one, we got to find the average. Right? So just take your calculator, take 0.865 plus 0.935, hit enter, and then divide by 2, and hit enter again. And what do you get? I'll do it too. I'm getting 1.8. Wait, I forgot to divide by 2. 0.9. We're getting 0.9 straight on for the average. So I just literally just typed that right there. Everybody see that? I just put that right there. That's the center. That's the average. That's the 0.9. That's the middle of 86% and 93%, is 90% right on the button. And now, give or take what error amount? How do I find the error amount? The error amount will equal the average minus the small number, huh? Because 0.9 is right in the middle of these two, isn't it? Right? You get what we're saying? When we add them and divide by 2, we get the middle. So 0.9 is right in the middle of those two numbers. So if you want to know how far from the middle, back and forward, you just take the middle, 0.9, and subtract the smaller number. And that comes out 0.035, right? 0.035. And we got it. We'll do another one of those. Is that making sense? So we're saying 0.9 is the middle, give or take 0.035. Those two statements, and the news will often say it that way. They'll say 90% of the families in whatever, Stanislaus County, 99% of the adults have kids, give or take 3% error. And that's what they're saying, which is the same thing as saying the real confidence intervals between 86% and 93%. Same thing. And they'd say there's with 90% confidence. They don't always say the confidence level. Some say leave that out. But there is a confidence level there. It's never 100%. Okay, 128 students at a college were asked whether they had completed their required English 101 course. Have you completed your English 101 course? English 1A is what we call it, huh?
Yeah.
And 96 students said yes. Find the best point estimate for the proportion of students at the college who have completed their English required 101 course. round to 4 decimal places. Yeah, no percent. It never said 90% confidence or 80% confidence. It just said find the best point estimate. That might be a confusing phrase. Just what if I asked you, just try to be, again, like I always say, try to be real with this. Just all fancy stuff aside, what if I just said, hey, a study was done on our campus here, and 128 students were asked, did you finish your English 1A course? 96 said yes. What percentage do you think have really finished their English 1A course at our college? What would you do? Yeah, you would just go 96 divided by 128, right? Because, 96 out of, we did a little survey, and 96, in our little survey, 96 out of 128 said they had. So isn't that what you would do? That's exactly the right thing. That's all you got to do. 96 divided by 128, you would get 0.75. 0.75. So we're saying in our little sample, 75% of the people had completed their English 1A. So we think probably about 75% of the school. We know there could be some error, but we're not going there. We're just saying we think about 75%. That's all they want. So they just want the main thing there. They don't want anything else on that. It's actually less work on that one. Does that make sense? Just divide the numbers. All right, we'll try 7. Assume that a sample is used to estimate a population proportion P. Find the 95% confidence interval for a sample size of 324 with 254 successes. Enter your answer as an open interval, parentheses, using decimals, not percents, accurate to 3 decimal places. Bunch of fancy talk. They want you to do a CI, a confidence interval, so you know what to do, right? Go to stat, go over to tests, hit enter, go on down to the, whatever it's called, the one prop Z interval, and hit enter. And then it'll ask you for an X and an N and a C level. So what's our X? So what's X on this one? How about this? We've only got 2 numbers, huh? One of them has to be X and one of them has to be N. Which one's always bigger? N's always bigger because that's always the total number. That'll be like the rest of the semester. N is always the total number. It's always the bigger number. So and it even says sample size, doesn't it? Sample size of 324. So that's our N. The other one, 254 successes. What is that? I don't have any idea. I don't know what they're doing. Maybe they're asking people if they finished their English 1A class, and a yes is a success. I don't know. They're not giving us the details. And then the confidence level, 0.95. Hit the buttons. I'm getting point, and then with 3 decimals, 739, comma, 0.829. Rounded, it was 2876. So I rounded to 29. That's all they want. They want the actual parentheses with the 2 numbers and the comma is what they're saying. Open interval parentheses. And not percents. They want decimals, so I just left it as decimals. Good. I'll try number 8 there. They're wanting you to take this and write it as an interval. Give you a second. So if we take a 0.292 and we give or take 0.033, so then you just go minus 0.033, comma 292, add 0.033. Is that making sense? See what they want us to do? Because it's 292, give or take, add or subtract, error amount, 0.033. So just use your calculator. I'm getting 0.259, comma, 0.259. 0.325. So they want me to say 0.259 to 0.325. Is that making sense how we figured that out? Forms, there's the parenthesis form, and then there's the average and the give or take, error. Two different forms, saying the same truth. So try number 9. So they're giving me an interval. This is the same thing as parentheses, isn't it? That interval there. And they want me to go back to the average. This is going to be the average, right? And the give or take error amount. So can you go back to that way? Remember we have the 2 steps. Let me let you do that. All right, so we good on this? So whenever you want to go from like the 2 numbers, well, they're both 2 numbers, huh? Whenever you got, this is like the range, isn't it? This is like the parentheses, basically. 23.8 to 38.6, like that. Whenever that's the same thing as this. Whenever you want to go from that, you've got to start by finding the average. And so to find the average, you've got to add them and divide by 2, huh? Because that always gets you the middle of 2 things. So just add them, hit enter, divide by 2, hit enter, and I don't know what that is. I'm getting 31.2. So 31.2 is the average of those 2 numbers. It's the middle of those 2 numbers, like averaging 2 test scores or quiz scores or something, right? Just add them and divide by 2. And then how do you find the error amount? Yeah, if 31.2 is like the middle of the 2 numbers, then you want to know how far from the middle back and forward. It's going to be the same amount. So you can do it 2 different ways. Yeah, you can do it 2 different ways. I'm going to take the middle one minus the small, right? So the error will be the middle, the average, in other words. The average number, the middle number, minus the small. So 31.2 minus 23.8. What is that? 7.4. So the error amount must be 7.4. In other words, 31.2, give or take 7.4, is the same thing as 23.8, take 38.6. 2 ways of saying the same thing. You could double check when you're done. Say it was a test question, you want to be sure. You could just take 31.2, subtract 7.4, you should get that. Add 7, right? The add and subtract options. Just do those 2 options. Just add the numbers and then subtract the numbers. You should get the 23.8 and the 38.6. It should go right back. If not, then something's wrong. Make sense on that? Okay, good. So, and then number 10 is more of the same, right? You just do the add and subtract there. You crank that one out.